Okay, so what you're trying to do is prove this fact that for any n cross n doubly stochastic matrix, Aij non-negative, summation Aij for all rows, all columns, the sum is 1. And the permanent is at least n factorial over n to the n. So the thing I will do is that instead of A, I will assume that all entries of A are actually strictly positive. And how can I assume that? We'll assume that Aij is strictly positive. And how can I do that? Just by doing this. So replace A by alpha A plus 1 minus alpha J by n. J is the all ones matrix, right? For alpha in 0. So for any such alpha, for any alpha in 0. Okay. So for any such A, we now all the entries of Aij are positive. It's still doubly stochastic and everything is there. Everything we did goes through. All of this is fine. There's another thing now that all the terms, actually all the terms are positive. So in particular, so yeah, so this assumption now, because we are even assuming that the Aij's are positive, so then it's even easier. In fact, the degree of xi in fi is 1.
Sorry, Piyush. Hello?
Not just that, but the degree of
Hi, Piyush, can you hear me?
xi. So let's just think about this, why this is the case. So how was fi obtained? So remember, so we started off with fn. Fn was the whole of gn. What was g? G was this product of monomials. Right? So for every row of A, you had a monomial, and then you took the product. And the variables appearing in all the rows are the same, x1 to xn. You took this product. Okay. So now what was happening here? So so by the time I get to xi, I have differentiated and then set to 0 all the variables except that appear after I. Right? So I plus 1, I plus 2, all of those variables have been removed. How have they been removed? They have been removed using this operation, where any term in which, so when that variable is removed, what that means is that any term in which the variable appears with degree 1, there the degree of the variable is dropped by 1. So it goes away and the term is retained. If it's anything else, then it's just dropped to 0. Right. So why is the degree of fi in xi 1? Because consider the term that is xi to the power I, and then after that all the other variables xi plus 1, xi plus 2, so on till xn. So this has degree n. Right? So this term exists. The reason it has non-zero coefficient is because Aij's are positive. And this term will survive all these operations because all of those variables will keep going away and only the xi to the power I will be.
Piyush, can you hear me?
Okay.
Hello?
Yeah, we can hear you, Akadev. I'm not sure.
Is someone saying something that I can't hear anything?
Yeah, I don't know how to get to Piyush.
Yeah, now I can hear it. Now I can hear it.
Okay. So can you hear me now?
Yes.
Okay. Sorry. I mean, I'm a bit confused. So why do you, so why did you need to perturb, change A to B the way you did? Because if we are only bothered, I'm probably missing something because
no. So all I want is, I also remember the issue was that we couldn't ensure that the degree of xi in fi is equal to I when we were doing this argument.
Right.
So now I'm ensuring that by just perturbing A.
No, but I thought that okay. So actually, I thought that the degree of fi is D. That continues to be true.
Yeah, also, degree of fi being I continues to be true, but we want the degree of xi in fi to be also I.
Yeah. That's true, because otherwise you won't get because you substituted everything else. That's right.
Yes.
Yeah, but this xi to the power I term in the original, if you just took A and not B, That term is still there, no?
No, but the thing is that corresponding thing might have vanished. It's like take the diagonal matrix, for example. That's the issue. So in the diagonal matrix, only the x1 to xn term is there. Every other term is
gone. Right. Okay. Yeah. Sure. Yeah, you said that the last time.
Yeah.
Correct. Yeah.
Piyush, I also have a question. So this might be silly, but I'm sort of wondering, why do we substitute xi to be 0? Because in the end, when you take all the partial derivatives, whatever survives is the permanent, irrespective of substitution.
Yes, that is true. So maybe you can even get around that. So the reason is I want to not have to deal with the other variables after that. So because those variables have not set to any values. Yeah, you can do the argument that way also, but I have not checked.
Okay.
Yeah, this way there's a nice thing that fi is only a polynomial in the I. So you've completely forgotten about the following variables. Okay, so now the degree of xi in fi is equal to 1. Okay, so yeah, so that's what we assume. So so remember that we replaced. So this note was not there last time. I have added it after that. Remember that we replaced a by this alpha a plus purchases. This ensures actually it's strictly positive, right? And we will so after doing all this argument, we'll get that the permanent of alpha a plus 1 minus alpha j over n is bigger than or equal to n factorial over n to the n. But we'll get this for every positive alpha in 0, 1. And so you take the limit to the left hand side, you get at least the weak version immediately. So that's the one we wanted to prove. Okay, so this is the thing. So then we have this proposition which we have not yet proved, but we'll prove today, that if you have a univariate polynomial, ai is non-negative, a1 and ad are positive. So the coefficient of the highest degree term and the coefficient of the linear term are positive, and it is real rooted. Then for all epsilon positive, there is a t in 0 to infinity. So there's some t. So the crucial thing is f prime 0 is at least d minus 1 over d to the power d minus 1 times the infimum over positive t f t over t. Another more like a easier way of writing this is that there is some, for every epsilon, there is some t such that this is bigger than or equal to ft over t times 1 minus epsilon. So I'm assuming that a1 positive, that is the same thing as assuming that f prime 0 is also positive. Okay, so now let's fix some epsilon positive, some arbitrary epsilon positive, small, and define. So now we start doing the same thing. We define s1 equal to 1, s2 satisfying that this derivative of fx2 is so this is again degree of x2 in f2. Okay, so this is now applying the proposition to f2. You have to check one more thing, that the linear term is non-zero, but that can be checked again. So yeah, so then you get this. So again we used all this a positive. Okay, good. So now given the same argument can be done iteratively. So suppose I'm given s1 to si. How do I define si plus 1? By applying the proposition to this thing. So I look at fi plus 1 with si s1 to si fixed, and I'm looking at the variable xi plus 1. The degree of xi plus 1 is I plus 1. Right. So yeah, so when we substitute this, I get I over I plus 1 to the I, 1 minus epsilon, and fi plus 1. Okay. So this I get at the ith step of this. So when you chain all of these together, so remember, what are we getting? So f1 s1 is bigger than d1 minus 1 d8 d minus 1, f2 s1 s2 s2 1 minus epsilon. Then you take f2 and to that apply this, so you get this. So if you see that, what you get is the permanent of a, which is f1 s1, is bigger than 1 minus epsilon to the power n minus 1. Product from I going from 1 to n minus 1 of I over I plus 1 to the I. So these are these terms that you're getting. And here you get fn s1 to sn, and in the denominator, the product of all the si's. Okay. which is just by definition 1 minus epsilon. So this you just simplify. So this is just n factorial over n to the n. Why is that? So notice that when I becomes n minus 1, you get n to the n in the denominator. And then the numerator, you are always getting the last. So you get n to the power n minus 1 in the denominator. And you're getting 1 to n minus 1. So what you're getting here is n minus 1 factorial divided by n to the power n minus 1, which is the same thing as n factorial over n to the n. So this is just a check. Is that fine? So yes, the reason I want to emphasize is this is where the thing is coming from. Sorry, is this question?
No, I said it's okay. Yeah.
Yeah. Okay. Yeah. Good. So now the only thing that was left is this thing. Since these are also referred to as capacity, but let's not worry about. This is the place. So far, we've not used stochasticity at all. Only thing we've used is positive entries. Okay. So now we bring in the W stochastic thing. So now we want to bound what is this term GS1 to Sn. All we know is that SIs are positive. That's all. So GS1 to Sn is what? So by definition, it's I this thing. Then you apply the AMGM inequality to this. Remember that summation Aij over J is 1 because of row stochasticity. Row sums are 1. So you get this.
Sorry, Piyush, I just got a bit. What? Oh, right. No, it's fine.
Yeah. So Sj to the power Aij. Then you collect the terms correspond to Sj. So you get Sj to the power I going from 1 to n Aij. But this is also 1 because of column stochasticity. So this is. Okay. And so you get that this so-called capacity is at least greater than equal to 1. So you get the permanent of A is bigger than 1 minus epsilon to the n, or n factorial over n to the n, for every epsilon positive. Because we remember we did this argument for any positive epsilon, and so you get it. You get the findings. Okay, so the thing was more or less at some point it became a machine. The main sort of the innovation was to actually come up with what the polynomial is that you should start with, and what are the operations you do. Right. So the operations to do also, or maybe, I mean, once you have the polynomial, maybe it's clear that these are the operations you have to do. So the main insight, in some sense, is coming up with the idea that you have to start with this simple polynomial, and then. So the rest of it, in some sense, well, okay, there is also this proposition which you have to know, right? I mean, so that's where all the calculations happen, this univariate one version. But from there to the multivariate case, the main insight is, in some sense, coming up with the right polynomial. So any questions about this?
So can we almost, is it the case that the proof goes through with matrices which like with different constraints on the row and column sums?
Yes, everything goes through. So the thing is that, so whatever you will get, so prove something is proving something more general. It's proving that the permanent of A is at least whatever this number times some capacity, right? So like the maximum overall S1 to Sn of this quantity of that. So whenever you can bound that, you are good.
And this would have also worked for rectangular matrices, right? Like there is no, it need not be
so
square.
Permanent.
I mean, you will have to just like define surjective functions from rows to columns. Like you could have.
Right. Yes.
Yeah.
Surjective functions from rows to columns. So the number of columns has to be smaller than the number of rows. No, so I'm not getting. So what?
I mean, I'm saying that maybe in a rectangular matrix, the generalization would be like every like you take basically all, like if it's an n cross m matrix, you consider m sized permutations, which I mean, where you are choosing different rows and different columns.
Yeah, I think that should also come. That should also.
I mean, the number of columns is more than the number of rows, let's say, and then you go through all injections. No?
Yeah.
Yeah. But that's usually the definition of rectangular polynomial. Yeah.
So then you will have one variable per column. So the number of variables is now more than the number of terms, right? In the definition of this polynomial. Is that an issue? Probably not. So it's still homogeneous of degree equal to the number of rows. There are many more highest degree terms. Yeah, so then there is some issue, right? So where do you stop this thing? Yeah, but I guess you could do something similar, but yes, I'm just not seeing exactly where you. So then now there are more variables than so the degree is not equal anymore to the number of variables. So this operation will not work, but maybe something else. This will kill off everything. Right? Yeah. So,
but is that true? Like
yeah, this will kill off because there are more variables. So I mean, the point is that every term. So the highest degree terms correspond to size I subsets of the variable. So let's say it's R cross C. R is less than C. So the highest degree terms correspond to R size subsets of the C variables. So each one of those terms is killed by this operation if you differentiate and set to 0 all the variables.
Okay.
So yeah, so something. But yeah, but this idea could certainly be generalized. I think. So I think Gurwitz's paper already has some. It's not just this. There's more in there. So okay. So now the thing is to prove this proposition, and also just to recall that we did this with. We did this with perturb with a perturb A. Perturb version of A, which is Wilson's inequality. We get the inequality for A as well. Okay, so the next thing is to prove this proposition. So modulo this. So I'll actually do this more or less, I think. And so modulo this proposition, we are done. Okay, so the proposition also will be not hard. So okay. So how will you go about this? So suppose that we assume that f is real rooted. So let R1 to Rd be the roots of f. Okay. So for now, let's assume that 0 is not a root. Okay. So assume 0 is not a root. Okay. So assume for now that. So this is a situation. This is a situation we are in also, by the way. Why is that? Because of permanent A 0, non-zero, and so on. So, but yeah, for now, let's assume that R1 none of them are 0. So now let's just do the factorization. So fx over x is just like I just multiply out x. So actually the roots are what I meant was like minus r right, and I factorize them as AD over x. I go from 1 to 2 of x plus r right. Okay, ri's are non-negative, right? So they are less than equal to 0 because the coefficients are assumed to be non-negative and the roots are real. So as we saw very early on, that the roots therefore have to be non-positive. So you have this factorization. And then I want to claim that this is actually less than this. So let's just see that. So for now, let's assume this. So this is just AD over x. I can x plus r. which is equal to AD product over I going from 1 to D of Ri over X. Then I going from 1 to D of 1 plus X over Ri. But what is this AD times the product of I equals 1 to D of Ri? It's a constant term of f of x, right? So it is exactly equal to f of 0. And when x is non-negative, we can apply AM GM to this to get that this is less than or equal to. Okay. We are always working with x positive. Okay. But what is this? So this is just this 1 over Ri is just f prime 0 over f0. So this is also easy to check. The simplest thing to do is to just notice that f prime x over fx is just summation 1 over x plus Ri. So that's the simplest one. Okay, so let gamma be equal to f prime 0. So right now I'm assuming that, so if none of the roots are 0, that also means that f of 0 is not equal to 0. Okay. So this is well defined, and it's actually positive also, right? Because why is it positive?
F prime 0 is positive.
Yeah, because we assume that A1 is also positive. So what we have so far is that fx over x is less than or equal to f0 over x times 1 plus gamma x to the d for every x positive. Okay. So now what we do is try to minimize the minimize this right hand side. Right? So what is the minimizer? So this is true for every x. So in particular, the inf of fx over x is less than in over x positive, x positive, x, okay. But what is this thing? So this we can just do calculus, right? So the minimizer of the right hand side is a solution of so this is the log derivative of the log, exactly. That's exactly what I've written. So it's like d gamma x. And this also shows, this form the derivative also shows that this or the above calculation of the derivative also shows that this is actually a minimizer, not a right? Because below x the derivative is actually negative. after x, the derivative is positive, so it has to be minimized after this value. This is easy to important to check out, but also easy to check. Okay, so now we put that thing, so we get that d minus 1 and 1 plus 1 over d minus 1 to the d. When so our assumptions are that gamma is positive. So our assumptions are so let's write our assumptions. F prime 0 positive and f0 positive. Okay. The first one is from the hypothesis. The second one we have just assumed for now. But this is what? So this is, so gamma had a form, right? So gamma was f prime f0 over d, right? So this becomes f0 over just f prime 0, and this becomes d minus 1 over d, and this becomes d over d minus 1 to the d, which is just equal to f prime 0 d over d minus 1 to the power d minus 1. So we get that when f0 is positive, then f prime 0 is bigger than or equal to d minus 1 over d to the power d minus 1 in fx over x. Okay. And the 1 minus epsilon statement then follows because everything is positive. So we're okay. So this was assuming f0 is bigger than 0. This is the only case that matters for us because we have this property. Because the f0 thing for us, this is the constant term. It always corresponds to the permanent. So that is non-negative. So that is fine. But yeah, but you can just see what happens when f0 is actually equal to 0. Then this infimum of ft over t is what?
A1.
Yeah, which is exactly f prime 0. Right?
Screen got stuck, or is it just?
Sorry?
No, the screen had got stuck for something.
Screen had got stuck. Okay. Now it's fine. Now can you see?
Yes, it's not. Yes.
Because this factor is anyway less than 1. So. Okay. So this is right. So this So this finishes the proof of the group. This finishes Gurwitz's proof of the of the
Piyush?
Yeah.
Yeah.
Mhm.
So if we look at these doubly stochastic matrices, I mean, they are the convex hull of permutation matrices.
Yeah.
But so is the permanent as a function over this polytope concave? Sorry,
No. Permanent, I
convex.
think, is not like that, but you can get similar behavior because it's multilinear. So you can.
So are there local minimas other than this?
No. So the stronger thing is known. With that, this actually there's only one local minimum of this. Yeah.
Okay.
So, yeah. So that's what Igor Ezio proved. Yeah. The J is the unique minimum.
No, but it could have local minimas. This is the global minima, right?
Oh, that way. That I have not thought about. But okay. Yeah, that I have not thought about. But maybe that's something that can be checked, right? So can't you just write down the derivative and see something like that? Yeah, I'm not sure actually. Yeah. So it's not convex. I think it's probably easy to prove that it's not convex. Maybe even in 2 dimensions or something, right?
Oh, okay. Okay.
What is true, I think, is that you can often get it as a convex. I mean, at any point inside, you can express the value as a convex combination of the values. I mean, that is not saying anything, right? I mean, it's no, that says something. It's less than or equal to that. No? Because of multilinearity. Yeah. So let me not speculate on that. So I don't know the answer. Check.
Okay.
Okay. So any more questions about this? So this implies that.
So Piyush, was this the first major use of Gurwitz? Sorry.
No, I think the second thing I'm going to talk about is older.
Oh, okay.
I mean, so. So basically, I think the probability use is probably older, like things like negative association, that kind of thing.
Okay.
In theory, of course, much older and like.
Gurwitz's proof is from the 90s or what?
I think 2006. I think.
Oh, 2006. So that.
I think so. But I might be wrong. I think it's a stop 2006 or something, or maybe sometime around that mid 2000s. I think. Wait, maybe you're right. 90s. Okay, but let's check that off. I think it's 2006, but might be wrong.
Piyush?
Yeah.
Sorry. So can you tell, like, where did we use stability of the polynomials in this proof? I'm a bit lost.
Yeah. Okay. So let's see. So where did we use stability? So we started off with a stable polynomial. At every step we had stability, and we were using. Okay. Yeah. So where did we use stability? Good.
Step we used that
Yeah, that's actually I forgot to mention it. No, at every step. The point is that you always use the fact that these FIs are real rooted. Right? I always, so how did I get to apply the result?
Yes, right.
Oh, I
So
see.
where,
The
so
proposition is for
so these guys are all real rooted. Why are they real rooted? Because I took a real stable polynomial, the FI, and I substituted some of them to be real values, and we showed that, right, that when you real stability is preserved by setting things to reals. So this Fi with S1 to Si fixed is also real stable, and because a univariate polynomial, it is actually real rooted because it has real coefficients also, and hence you can apply this proposition.
Okay, thanks.
Did I never write it out? Okay, I sort of implicitly was there, but yeah, this is the point where you're using it. Okay, so any more questions? Okay, so now let's look at a different problem. So this also I showed in the beginning of the class that so we have another counting problem. So G is an undefined graph. ST of G is a set of spanning trees of T, and now we choose one each spanning tree uniformly at random from this, and then I ask for fixed edges EF of G, do we expect that the probability when of this edge being, so we choose the edge from like probability that E is in T times the probability that F is in T, whether it is less than equal to or greater than or equal to, so the probability that E is in T and F is in T. So I think Sayantan and maybe others also had guessed that the inequality should be that the product of the marginals is what? Is greater than or equal to the, yeah. And the rough intuition was that, well, when you put an edge in the spanning tree, somehow other edges are less likely because they might create cycles. So that was the rough intuition. So there are other ways to prove this, but we'll do a proof which will prove other things and also as a corollary imply this. And it will also let us go into some very interesting 19th century mathematics, which also is relevant today. So, and we'll be looking at, so the relevant polynomial we'll be looking at is the following polynomial. We put a variable for every edge of the graph, and then we look at the spanning tree polynomial, which is that for every spanning tree, for every spanning tree, I have a product of the variables corresponding to the edges in the spanning tree.
This is a spanning tree polynomial. It's called the spanning tree polynomial, right?
I think yeah, it is, but
yeah.
It's a generating polynomial. This is a natural generating polynomial of spanning trees.
So it counts the number of.
Yeah, if you put x equal, all of them equal to 1, it counts the number of spanning trees.
Yeah, so that I think is called the spanning tree. It's very well studied. Yeah.
Yeah, it's a very well studied polynomial. Yeah, and yeah, so we will now start studying this polynomial. So the main theorem. So yeah, here. So we will actually prove this. This is from an earlier version of this where I was not going to prove it. So, but the theorem we will prove is that it is actually real stable. And doing this will go through Kirchhoff matrix theorem also, which is about the 19th century thing I was talking about. And it will also introduce us to one class of real stable polynomials, which is like, in some sense, yeah, it's the most rich, not rich, it's like the most fertile class of real stable polynomials. So that many real stable polynomials that you come across will have come from that class. So we'll see that. Okay. So, but why is that? Why would real stability help? So let's first do that. Why? Suppose let's assume this theorem for now, and let's see what we can do with it. So let's try to write, because a generating polynomial, you can do some things, right? So so let us try to write these probabilities in terms of the generating polynomial. Okay. So I want you to take these two things as exercises. So first thing is the probability that, okay, maybe the second one is first, the probability that E is in T, the edge E is in the spanning tree, is just, I take the derivative of this tau with respect to XE and then set every variable to 1 and then divide by tau. Okay, why is this the case? This is standard genetic function manipulation, right? So you have all these objects. The objects that have E in them have the variable XE. So when you differentiate, only those objects survive. So when you set them to 1, you count only those objects, and then you divide by the sum of the count of all the objects. So this is exactly the probability that E is in T. Similarly, what's the probability that both E and F are in T? That is that you take this polynomial, differentiate with respect to both E and F. So now only those terms objects survive which have both E and F. Right? And then again you set all the variables to E, go to 1, and then divide by tau. So these two are just okay. Okay, so is this fine?
Yes.
Okay. So now we will look at a bivariate polynomial that is coming. So okay, so I'm assuming all this while the tau g is real stable. Now we look at this bivariate polynomial, which is the following. So I put ones at all the positions except I have two variables u and v, and what I do is that at xe position I put 1 plus u, and the xf position I put 1 plus v.
Piyush, hello.
Yeah.
I'm just a little confused about this bivariate thing. So no. So you started with a graph G, right?
Yes.
And you looked at the spanning tree, but the tau underscore G was the spanning tree polynomial for that graph G,
yes.
Right?
Yes.
Yeah. No. When you go below, when you were defining this HUV, the bivariate thing, you have one every. What does it? I mean, so
which are the variables of this polynomial? There was one variable for each edge, right?
Yeah.
And there were two. Okay, so maybe this is the confusing. So I'm using E as also the generic name, right? So I have these two special edges, E and F, which I'm interested in right now.
Correct.
Right? For which I take all the other edges and I set their variables equal to 1.
Yeah, all the other edges of this graph. Of course, the edges that were absent in the graph G, they are not there.
Yes, they I mean, I can set them to 1 also, but that doesn't that will not matter.
Yeah. Okay.
But for these two edges, I have two variables u and v. So I put 1 plus u in the xc position, 1 plus v in the xf position. Okay. So the first claim is that HUV is also real stable. Why is that? So certainly,
if I just HUV is also. So what did you already say?
So I assume that tau is real stable.
Oh, you're assuming tau.
So you're substituting a real number at each step. So
yeah, so you're substituting a real number at each step, and then this issue of translation. Translation also preserves it, right? So then.
And translation, as long as it does not affect the imaginary part.
Yeah, exactly. So real translations preserve it. So that is also so HU is real stable because tau is real stable. Okay. And now here is one more thing, and this again is an exercise which is easy to see. Is that you can so it's a bivariate polynomial. What is its degree, by the way? What's the degree of this polynomial?
At most 2.
Yeah, at most 2. Let's say if both the edges, at most 2.
If they are parallel edges, then it is 1. Otherwise,
yeah, good. So but actually, so what Shreto is saying is what you want. So you can actually write down. So you can see that when the constant term of this is actually tau 1, that you can easily see because you just put u and v equal to 0. That's the constant term. Tau is 1. The degree is at most 2. So the linear term, you can show that it is the d. So is the derivative of tau, and then so first is the derivative with respect to the xe variable of tau, and then put 1s everywhere. That's what this means. And then the v variable is where you do the same thing with f, and the uv term, the quadratic term, is when you take both the derivatives. Okay. So this is just okay. So this is, I mean, I don't want to say that you see this immediately, but it is reasonable that this is true, and it should not hard. It should not be hard to prove. So which are the, so what is this? So yeah, so how do I get to this term for u? One way to do it is to first set v equal to 0. Then it is just tau 1 1 1 1 plus v 1 1. All of them are 1. And then that tau is certainly at most a linear polynomial. So the coefficient of u must be just the derivative, right? Which is what this is. Similarly for v, and this one is also similar. Okay. So this is just this is just you just write it out and you see. So this is not a. It might help to sort of shift the whole tau thing. So these ones are maybe not nice. So if you just shift all the ones, so you define a new polynomial where every variable is shifted by 1. Then this is just a Taylor expansion of h around 0. Yeah,
no, but why can't you do it just simply observing that, you know, I mean, the only way this u will appear is where, I mean, you know, in all the monomials, which each monomial corresponds to a spanning tree, right? Yeah. And in all the monomials that contain the edge
u,
xc,
yes.
Yeah, and basically the count of those many edges is exactly by the generating function trick, the derivative of the, so
yes,
you get that.
exactly. Yeah, so there's many ways of seeing this. Yes, so that, yes, I'm not telling you this is anything non-true. So this, yes, I'm just saying that after some. So it's that old joke, right? It's like it's trivial after 2 minutes or 5 minutes of thinking, and it's
no, but I don't understand why this will be non-zero. I mean, because it could be that there are no.
Yeah, this need not be zero. So right now I'm just saying that this is just true. Some of these coefficients might actually be non-zero. While actually be 0, that's fine. But they're there. But tau 1 is certainly non-zero, right? So this polynomial as a whole is not 0.
No, that's true. But
and there's also always a spanning tree containing. So the linear terms are also non-zero.
Why there may not be a spanning tree containing the u term? No.
No, you can always make it, because you just put a weight. I mean, it is always a spanning tree containing any edge, right? Because you just add that to the edge and remove some.
Because we assume the graph is anyway connected. I'm sorry.
Yeah.
Otherwise.
There is a spanning tree we are assuming. Yeah.
Oh, sure.
Yeah. Otherwise, none of this makes sense. So at this second term, as Sridhar was pointing out, might be more complicated. But let's not worry about it. So, okay. So now we ask, when can such a quadratic polynomial be real stable? So we know that it is real stable, assuming tau is real stable. So we ask, when can it be real stable? So let's write. So these, we have just 4 numbers, right? Like 4 constant numbers. So we have some polynomial which looks like axy plus bx plus cy plus d. We know that those numbers are non-negative. Okay. And I'm assuming that b is not 0. So actually we can assume even that b and c are not 0. Let's assume that b is not 0. Okay. And now I want to see when can this be real stable. So let's see, when can it be 0? So suppose this polynomial is 0. Then x has to be, so just by substitution, x has to be minus cy plus d divided by ay plus b. Right? Okay, this is fine, right? This is just this. So now here is the thing we want to do. So we want to say that. So we want to prove that it's. So we want to understand when is it real stable. So what does real stability mean? So in a bivariate case, it's something very simple. Right? All I have to show is that whenever y has positive imaginary part, x does not have positive imaginary part. Right? That's what we have. So it's real stable if and only whenever you put y to be positive, y to have positive imaginary part, this x must not have positive imaginary part. Then and only then is this p real stable. Is that fine? So let me assume that.
Sorry, I got a bit confused.
Yeah, so the point is that this P is real stable if and only if only if im y positive implies that the imaginary part of this minus cy plus d ay plus b is okay. Because I put any y, so is this comment clear? So let's see. So if and only if, right? So we have two directions. So P is real stable. Why is this? So suppose that the thing in the bottom is true, right? Now suppose that there is some root xy where both x and y have positive imaginary part, but then y has positive imaginary part. But then this thing implies that x has to be minus cy plus d, ay plus b. But that therefore implies that the imaginary part of x is non-positive, which is a contradiction. Okay. So if P is real,
Sorry,
Piyush,
Piyush, I think you went a little too fast for me.
Yeah, so let's just do it again. So assume P is real stable.
Yeah.
So or rather the other way around. So suppose okay, so the other way around. Suppose
there is a zero in which both x and y have
positive imaginary part. Positive imaginary part. Yeah.
So I'm a bit confused here. So real stable means I mean no. Suppose there is a root in which one variable has a real imaginary part, but the other doesn't. That is permitted.
That is permitted. So a polynomial is real stable if whenever all variables are have positive imaginary part, it is non-zero.
Then only it okay.
Yeah. Yeah. Okay. So let's just do this. Maybe write it out. Yeah? So why? So suppose P is real stable. Let y be such that im y is positive. Then P minus cy plus d ay plus b y is equal to 0 by construction, right? So by real stability, we get that im minus okay, so this is one direction. Second, suppose for every y such that y positive sorry, listen. No. Suppose x, y are such that x, y equal to 0 and imaginary part of y is positive. Then x is equal to minus cy plus d ay plus b, so that so both arguments cannot have positive imaginary part at any 0. Okay. Is this fine?
Yes.
Okay. So now we are in good shape. So now we are seeing that P is real stable if and only if imaginary part of Y implies imaginary part. So we have to just understand this condition. Now let's see. So what is this imaginary part of? So now what is this imaginary part of cy plus d? So minus cy plus d ay plus b. Remember, the A, B, C, D are non-negative, and B at least is, so B is non-zero. So everything here is well defined. So the division is well defined. So, and yeah, I am assuming that Y. So what is this? So this is negative of the imaginary part of Cy plus D, Ay plus B. And the standard trick here is to just make the denominator real. So this is equal to minus them, and so I just multiply by the conjugate. Remember that the reason I can do this, like I just put the conjugate bar over Y, is that A and B are by definition real. Okay. So now this thing is just a positive number. What about the numerator? So numerator is BD plus AC Y norm square, right? Plus BCY plus AD Y bar, right? So this part, this is the imaginary part of this is exactly is, so the imaginary part of this is 0, right? So we have to just go here. So this is what is PC times the imaginary part of Y. And what is the imaginary part of Y bar?
Minus.
Yeah, minus of this, right? So this whole thing is minus, so yeah, minus BC minus AD AY plus B whole square, imaginary part of Y. Okay. So when Y is positive, in minus this, whatever this thing was, CY plus D over Y plus B is less than equal to 0 if and only if BC minus AD is non-negative. Okay. So the upshot of all of this, that if, so the lemma is, so we have proved let pxy axy plus dx plus cy plus d equal to b a real stable polynomial. So actually I didn't even use, well, yeah, maybe let's just still keep it with A, C, D strictly and B is strictly positive. And then but what is this? What is this BC minus AD is bigger than AD in our setting? So applying this to H, I think H gives the probability of E times the probability. Okay, so we have the proof of the.
Wait. What? Sorry, how did you get that? So B.
Yeah,
and
okay.
C.
So what is B and C? So what was B and C in H? So B was just so except
Correct.
so okay. So there's a tau division by tau 1 happening, but let's forget about it for now. So this
That's
is like
right.
yeah. So let's see. So this is like the probability of E times tau 1. This probability of F times tau 1.
Yeah.
And this is like the probability of E and F times tau 1. And there's another extra tau 1. So the factors of tau 1 cancel. They're known to be positive.
No, but I'm confused because there are 4 terms there in that equation. No, B. I mean, sorry, where did you?
Yeah. So what is D? D is tau 1, right? So tau 1. Okay,
oh,
so
right. D
yeah,
is tau 1. Yeah.
The normalizer. Yeah.
Okay. Sorry.
Yeah. Yeah. So the thing you get is the number of this is times the number of this is bigger than number of these times total number.
Yeah.
So here the only property of trees we used was the fact that the polynomial is real stable.
Yes. And that
So
that's it. Yeah, that's it.
So in general, for any structure whose corresponding polynomial is real stable.
Good. Yeah, that's a good point. Yeah, so that is true. So any structure, so any generating polynomial where you have that the generating polynomial is real stable has this negative. So this negative correlation, actually something stronger is true called negative association. And yeah, so we'll do all this.
Sorry, Piyush, 1 second. Isn't there some famous graph theory conjecture called like Pseudorankos conjecture, which sort of asks something very similar looking? Or I'm just.
Yeah, I've heard the name. I can't recall what it is.
Okay, then forget it.
Yeah.
We'll talk about it later.
Yeah,
and you haven't proven the real stability.
No. Yeah. So the big thing in the thing is tau is, and yeah. So what I want to highlight is what Sridhar was also saying, that this is actually we use almost nothing about trees. We only use real stability. So this negative correlation, and in fact something stronger called negative association. You can do this not just with single edges, but like arbitrary sets also. Is a property of all real stable. So any probability distribution whose generating function is real stable will have these properties. Right. And in particular, notice something interesting. Suppose we prove that tau g is real stable, then differentiating tau g with respect to another variable also it will be real stable, right? But what does differentiating mean? Differentiating means conditioning on the edge being present. So this is completely, this is something a priori extremely non-trivial, right? That this negative correlation property will be preserved even if you condition on an arbitrary number of edges being present. In fact, not just present. How do I condition on an edge not being present? By just setting that variable to 0. That also maintains real stability. Right?
Well, that is because those correspond to spanning trees of the remaining subgraph, right? No, sorry, it does not.
No. So that is like contraction, right? So contraction is
yeah.
So it's a priori these are not so trivial, and this is not about trees at all. This will be true for any such distribution as this property. So conditioning will preserve this. So okay. By the way, having this property is not equivalent to real stability, but trees have a stronger real stability thing. So then it means that all these negative correlation properties are preserved even by conditioning. Conditioning on some edges being present, some edges being absent in some arbitrary combination, you still have the negative correlation present.
Did we use multilinearity of tau? Like, what if we have a
we use multilinearity, but yeah, that is fine. Like so all I'm saying so far is about generating distributions of genetic polynomials of multinomial distribution. So they will be multilinear. But yeah, so we are using multilinearity in that sense, but that is not any generating polynomial of multinomial.
So what does that mean? I'm actually not able to process. So any generating.
So what is generating? So what is happening here? So you have some subsets, right? So there is this ground set of edges, right? What is this right hand side? It's like a, so suppose I put a 1 over the number of spanning trees here. What is this? This is like saying for every there are like some subsets that cannot be realized, which are say cyclic graphs or graphs which have more than n minus 1 visits. So everything else has a subset can be realized with probability 1 over the number of spanning trees. So this is the generating polynomial of that distribution. But I can think of arbitrary such distribution. Right? Suppose I have some other distribution on sets. So for every subset of the edges, I have some probability distribution. I can write down a polynomial like this, which is we go over all the subsets. For each subset, I put the coefficient as the probability of that subset, and I put the monomial as the product of all the variables in the subset. This is a standard construction of the generating polynomial. So that's the situation we are in.
So okay, I see. So one thing which I'm confused about is in the beginning of this course you had talked about some polynomial which came out of independent Bernoulli coin tosses.
Yes.
That was univariate.
Yes, and that was a generating polynomial of a univariate thing, which is because that was a slightly different kind of generating polynomial because it was like a counting generating polynomial. So it was saying this thing can take values 1 to I, and I represent the value I with x to the I.
Got it.
Now I am representing different values of subset with. So how will you reconcile the two? So the reconciliation can come from if you take a distribution over the hypercube with a different variable for each position, and then set all of them equal so that the weight then the univariate thing will result, and the weight will be the number of elements in the set, something like that.
Yeah.
So that's the
okay.
Okay, so now we have to prove that in 15 minutes is already too little for this. By the way, this calculation I did about this imaginary things, this is completely unrelated to this course, but this fact, right? So this kind of a thing it might look like some hack that you first look at this kind of a function, and then you see when is it imaginary part, positive, negative, etc. But this is not that. There's something slightly more nuanced, slightly more principled going on. What these things are fractional linear transforms of the complex plane. So they take lines to lines or circles, right? So if you define circles and lines the same class of objects in the complex plane, then these transformations preserve that class. So any circle will be taken either to a circle or a line, and any line will be taken either to a line or a circle by such a transformation. And the sides will be preserved. So each side will be taken to the corresponding side. So all this is saying, so this is basically trying to, and so it's not surprising in some sense the imaginary part is preserved under a certain sense, because this linear transformation preserves the real line. So it can only take the positive imaginary part either to positive imaginary part, or it can invert it and make it negative imaginary part. So this calculation that we did, we sort of already knew that the answer is going to be something like this, that either under certain conditions, the imaginary part will always be positive, under certain other conditions, it will always be negative. So this also helps. So this idea of the fact that these, so this is a special class of transformation that we are looking at is useful, and it underlies many other calculations also. So including when you are doing stability with respect to circles also. And this calculation also underlies one way of starting to look at the geometry of the so-called hyperbolic plane. So if you're interested, you can see this thing. But we will not need this. So this is not an exercise anymore. We already proved it. Okay. So the generalization of this fact. So this thing I was talking about with conditioning, etc. They were used to improve Christophilus algorithm. So instead of Christophilus algorithm is this classic algorithm of Christophilus, of course, of approximating the traveling salesman in a. So you have a complete graph where the distances follow triangular inequalities, and the algorithm says that. So what does it say? So you first. So let me just. So you first take a spanning tree, and then take a matching of the odd degree vertices. Wait, something happened. Combine them and then short circuit the paths, and this will give you a 3/2 approximation to the best traveling salesman thing. So this 3/2 was improved by not doing an arbitrary spanning tree, but by sampling the spanning tree from an appropriate distribution. And in the proof that works, this played an important part. By the way, so and that's I think. By the way, so can you see my screen, or there's some issue here?
Yeah, I cannot.
Yeah, I cannot either. So something went wrong. Let's see. Okay, so yes, so this is the paper that you can see. Okay, so now,
Sorry, in the original algorithm, you just take a MST and find the minimum matching between the leaves, right?
Of the odd degree vertices.
Just a leaf.
I think
Obviously.
so basically you need to construct an Eulerian cycle and then
Yes.
and then
Routing.
short circuit to get a Hamiltonian cycle.
Yes.
Short circuiting is allowed because of triangular inequality, and the point is that because a Hamiltonian path is both a spanning tree and gives a matching, so this whole thing will be a 3/2 approximation. Yeah. Okay, so good. So we have done this. So the thing we have to do now is to prove that the matching. So what to do now? But I have only 10 minutes remaining, so I'll prove something different, and then we'll prove that this one to next class. So what I'll prove is something like this. So starting point is, this is the thing I was talking about. This is rich class of polynomials, which is very fertile class of real stable polynomial. So let A1 to An be some m cross m. So n and m are completely unrelated PSD matrices. So in particular, they are. So right now, let me also say that PSD matrices is the real entries. And yeah, symmetric. So if you assume, yeah. So symmetry is implied if you ask for PSD-ness with respect to complex vectors also. So that's why symmetry, but it's not implied if you only ask for PSD-ness with respect to real test vectors. So, but yeah, but we want symmetry. And let H be, S be an arbitrary symmetric matrix. It's not necessarily PSD. So consider this polynomial Px1. Then polynomial P x1, x2, xn is defined to be the determinant of the sum of S plus the sum of xi. Okay.
Hello, Piyush, you seem to be frozen.
Yeah, no, I just wanted to wait.
Okay.
Okay. So is this statement clear? So that A1 to N are M cross N symmetric PSD matrices, real entries, then S is arbitrary symmetric matrix, then this Px1 xn determinant of S plus summation xi ai is PSD. Okay, so how do we go about this? So so the proof will be more or less direct calculation. There'll be some trick because we are only assuming PSD-ness and not full positive definiteness. So some eigenvalues can be 0. So let's do this. So for now, let me assume. So assume that, let's say that an is equal to identity. So it's strictly positive. Because one of them is strictly positive. In particular, let's say it's equal to identity. So let's see that at least with that assumption, it's strictly positive. So let's see that with that assumption we can do it. So now let's say that xi is equal to ai plus I. Okay. So let's say xj is equal to aj plus I times bj. So I is now the complex unit. So maybe I should write this iota times bj. 1 is less than 2 is less than n. Each bj positive, bj real. Right. So now let's see. So what is p of this xj? Right? So what is this p of aj plus it is the determinant of s plus summation ai here, right? Plus iota times summation bj aj. Okay. Let M be in this matrix here. Summation bj aj, j going from 1 to n, and let T be this S plus summation. Then P aj plus bj is exactly the determinant of T plus I n. Right? That's what it is. Good. So now what can we do? Now something should strike. So what can we say about T? What is the best thing you can say about T?
Was it greater than equal to s?
No, not necessarily, because A's can be negative, right?
Oh.
A's are just arbitrary real numbers. All we can say is T is symmetric. What can we say about M?
Still PSD, right?
Yeah. In fact, we can even say that M is strictly positive.
Strictly, yeah. Strictly.
Because we assume that at least one of the matrices is strictly positive. Right?
Yeah.
In particular, M is invertible, right?
Yes.
Yeah. So then this is equal to right. So this is just okay. Now what? So P of aj plus I bj equal to 0 implies that det of M inverse T M inverse plus I identity is equal to 0. Now, can this happen? Remember, T is symmetric. M is PS. M is strictly positive definite. Can this happen?
What do you know about T? So what is the
T is symmetric.
So, Piyush, here, why does it even like if you take the bases E1 to En, this operator is not killing any of them. So, I mean, in fact, it's giving a full rank image. So its determinant cannot be 0.
Why is it full rank image?
So what is the, I mean, just the complex part of E1 to En itself, they are linearly independent vectors, right? When I apply this operator on the basis E1 to En.
So that's what I don't know yet, right? I mean,
Maybe I'm missing something. Okay, I'm not sure. No, I was trying to apply this.
No, so I mean, so the thing is, okay, so this can fail, right? If T were not symmetric. I mean, all this is saying is that all you need is that. So all this is implying is that minus I is an eigenvalue. So it's actually equivalent of M minus half Tn. But this cannot happen because this matrix is symmetric.
T has real eigenvalue, right?
Yes. Okay. So what we get is that, so we get that this P x1 to xn, that's xn, which is determinant of S plus summation I going from 1 to n, let's say n minus 1, ai plus xn en is real stable when an equal to identity. But then I just used, so, but that implies also that that this q x1 to xn minus 1 is equal to det S plus summation I going from 1 to n minus 1 xi ai, which is just p of x1 all the way up to xn minus 1, 0 is also real stable whenever S is symmetric here and ai are symmetric, real and PST. Alternatively, you could have just done the same limiting argument we did earlier for proving this real thing, or you can just do it this way. So this is the time to not have to do the continuity argument that we've already done. Okay, so yeah, so we have proved this. So we'll continue next time and get to spanning trees. But you can probably see how the spanning tree thing relates to this already. The spanning tree with Kirchhoff matrix theorem is related to some kind of determinants. So that should be. So,